Hi all, Wayne here. All right, various people have asked us to actually put together this video on the platform overview of as we use it for Nano-Escrow.pro. Provision operations, headed up by Ernst and Yaku, who you will be introduced to in other videos, right? Is the sole distributor of Nano-Escrow technologies. As such, we've been asked to put together a platform overview, and without further ado, let's get there. Vision Operations, we firmly believe that this is the right team with the right technology at the right time. We can take your business to a new level, we can make you extremely competitive, and we can assist you in disrupting your competitors to a point where you are going to attain a large part of their market share. We have a network of project managers, software architects, senior developers, senior DevOps engineers, and expert clinical and business analysts to assist you in this. This is a journey. I want to emphasize that we want to go on a journey with you in terms of radically transforming your business. If we look at our list of areas of expertise, people always ask this, and we have an extensive list. And the most important ones are our microservice architecture, Docker as a core technology, Kubernetes as our orchestration layer. We like to develop in either C# or PHP, but have got significant experience in other languages as well, from traditional C++, Java, those environments. We are extremely proud of the fact that we database agnostic, but prefer to work in either MySQL or MS SQL, Microsoft SQL. We use Redis and Istio to help us manage our environment. And we like to deploy on either Azure or AWS. We can deploy in virtual machines or running Kubernetes across that, or we can use the native fabric of those environments. Right, let's look at the limitations of traditional software architectures. We've all heard the old story of you phone some organization and you say, you need to help me with X, Y, Z, and the first thing you hear is, sorry, our services are down, can you call us back later? If you're really lucky, they'll offer to call you. But now, let's have a look at why these limitations are there. First of all, they're usually two-tier. If you're really, really lucky, you have a service on your server level as well. Now, for a while, people stopped developing software this way. And that was very, very good. Right? And we got to N-tier or multi-tier solutions. Really worked well. But what's happened recently with the plethora of new mobile apps out there built by youngsters who really don't understand proper architectures is we're back to this model. And that's why a lot of apps fail. And they fail dismally because they are not extendable, extensible, and they certainly are not secure, and they have all kinds of other issues. So if we look at the traditional architecture, or the architectures that we're dealing with at the moment, they're heavy. They're thick clients. Maintenance and distribution was a hassle. They're monolithic. Monolithic has a whole bunch of issues, the least of not being security, which I'll talk about now. The main problem is they're high in maintenance. Development takes a hell of a long time. You touch one bit of code in one place and it affects code in another place, and you have knock-on effects of a change. And I think that those of us that are experienced in these environments know about those issues. It makes the code complex because one piece of software is trying to do everything. It doesn't scale very well. Scaling is a real issue. Right, and you inevitably hear the story of, your volume is such, or your throughput is such, or one part of your problem is massive for 2 hours in the morning. Now you have to buy new hardware, bigger hardware, expand memory, make bigger networks. That's an issue. There's also another issue around security, which is very, very important. Usually when these applications get hacked, you get access to the whole application. So this is not a good way of developing software. In the next slides, I'm going to be addressing our methodologies for developing this kind of software. Okay, so let's talk a little bit about containers and containerization. Containers are isolated user space instances that exist in a computer virtualization. A number of containers will work together to form a solution. They actually look like physical computers from a program and a programmer's point of view. When we do containerization, the most important thing is that from development all the way through testing, all the way through best build, all the way through whatever environments, into operations, which is live, the same container is run.
So you've excluded all the difficulties associated with, I've developed this on Windows X and now you're trying to deploy it on Windows Y, and the differences between Windows X and Windows Y make your application not work in the testing phase all the way through to operations. So that's removed. Secondly, in containers, you can use any application development environment. ASP.NET, Java, JS, Ruby, Net, it doesn't matter. C, C Sharp, it really doesn't matter what you do in terms of your application environment. Your containerization engine contains this all. Your containerization engine can also be Windows or Linux based or even other operating systems based. Your deployment can be anywhere. It can be physical, virtual, or in the cloud. Physical on your own hardware, virtual on shared virtual machines, or in a cloud environment where the fabric of the cloud allows for containerization. So, to our innovation. And remember, we're trying to deal with delivering a solution from end to end, including all the business, with the total cost of ownership being the lowest. So what do we bring to the service? Firstly, and most importantly, it's the way we architect things. We are able to rapidly and frequently and reliably deliver large complex applications or portions of them. We solve the complexities and challenges of the microservice deployment using Kubernetes and containerization. And we need to attain the following goals. Our solutions must be highly maintainable and testable. Our services must be fine-grained, granular, very small bits that make up the solution. And our protocols between these bits must be very lightweight, easy to understand, and above all, completely standardized in terms of the modern way of developing software. Our solutions must be independently deployable and must be organized and adjusted to suit the business capabilities and requirements and the ongoing changes to the business architecture and capabilities. So what we do is we create mobile applications, desktop applications, and web applications. And I'm just going to take a bit of a sideline here. In the modern world, having a desktop application back at the office is just not enough anymore to be able to solve any problem. People are mobile. People need to be able to see at least a significant portion of the total solution on their mobile apps. They usually need to have the desktop apps back in the office for administrative purposes, controlling the environments, dealing with the back office administration required to keep complex environments together. And then whether people use apps to interact with you or web, it must be the same thing. So if we develop these client apps, we develop them very lightweight so that as the business changes, and let's take that back into the server. Let's take that as the server being the engine room of the business. As those business requirements change, we must be able to adjust the client applications with the least possible intervention. Enhancement to, let's say, a service A at the server level in a perfect world should not even affect the mobile app. Just new functionality should just be available in the mobile app or the desktop app or the web app. So if we look at the server and we replace the word server for a little while with a service or an application, what we do is we granularize everything that needs to happen in that application. Something, let's call it a service E, needs to talk to the database, make sure all the data hangs together, make sure that it's presented properly to a service A, a service B, and a service C in this case, with these arrows indicating that. A service B might do a totally different role, but it needs to communicate with service E, which knows what's happening in service A, right through to the database. We can have multiple databases. So, in short, if we granularize into 5, we've got an example A, B, C, D, E, F, so that's 6 actual apps that independently operate. It means that if something goes wrong with service C, or service C needs to be enhanced, we're only touching a small portion of the code because the interface from C to E and F is standardized and understood and will not affect service B or A or D. In that way, we can develop software very quickly, deploy it very quickly with a minimum testing time, and very seldom actually have to take an application down. So in a live application, replacing a service C right into the environment while the application is live is really not an issue. It's an issue of testing and an issue of deploying it correctly. Those are the principal benefits of going with a microservices and orchestrated architecture. Right, so let's discuss Docker a little bit more. Docker is a set of platform as a service products that uses virtualization to deliver software in containers. I just repeat what I said in the previous slide in case I didn't make it clear, right? The Docker container working on the developer's desktop is the same as the one that you deploy. So you've excluded a whole bunch of issues between the developer and the person who needs to deploy the software or your DevOps team. All containers exist as processes and use fewer resources than traditional virtual machines. Right. So if we compare the two types of architecture, being the hypervisor infrastructure type architecture versus the Docker infrastructure, the benefits become pretty obvious. In the hypervisor arena, you'd run a number of virtual machines, each with a single application in it, and each with an operating system running, and that was a pretty good way of doing things about 5 or 10 years ago, right? And people really understood this, and a lot of machines were developed that way. If you look at containerized applications, however, you have an infrastructure. You then deploy Docker in the infrastructure. Each Docker then has a host operating system, right? And then your applications are actually containerized as app A through to app F, right? Now, if you replace app A, right, you're not having to touch the guest operating system. You're not having to touch anything else excepting the deployment arena within which app A needs to work. If you need to enhance app A in a live environment, you would simply deploy a second version of app A into the same environment, give it a little bit of traffic, have a look at how it responds to what's happening to the clients. We're talking about high throughput environments, right? And if you're happy with it, we slowly but surely shut down the first version of app A. These types of solutions are exactly how the Google environment takes about 100 updates to their Gmail application every single day, and it's never down. It's exactly the same way in which Netflix, which is probably the biggest deployment of containerized and orchestrated solutions in the world, right, are able to be up all the time, but they're constantly putting in new movies. They constantly are updating their environment, and they take about 1,000 updates a day to their software. Very, very interesting. So containerized applications have got significant benefits, right, for business agility. Okay, let's talk a little bit more around Kubernetes. We as a software team are extremely proud of the fact that we were one of the first people or groups of developers outside of Google that actually deployed this. Right? We certainly weren't the first in the world to do it outside of Google, but we were certainly the first in South Africa to do that. And as such have become leading consultants to the rest of South Africa in terms of these technologies. It is significant to realize that this is 15 years of Google's development experience. I don't know how many millions or probably billions of dollars they spent on developing this, right? And they then open sourced it, right? And that's the modern way of doing these things. So if we have a look at orchestration, which is Kubernetes, together with containerization, which is Docker, an innovative way of developing software, of understanding exactly how to granularize your Dockers for a solution. This then equates to predictable, controlled, consumption-based deployment capable of worldwide scale. I want to talk a little bit around consumption-based deployments. What this means is you pay for the processing that you use. So in your less busy months or less busy part of a day, you're paying less than in your busy days. And that's a really, really important consideration in any deployment. Once again, we're addressing the total cost of ownership of a solution. The development cost, I'll say again, is actually a very, very small part of the total cost. Ask any financial guru, right, in your organization, and he'll support what I've just said.
Right, so you ask yourself, what are the benefits of our architecture? Our distributed, orchestrated, cloud-based microservice architecture provides you with isolation of code dependencies. What this actually means is that you could have one set of code running in a container that's using a stack, and let's say that is a PHP version 4. Not that any of us do that anymore, but let's say that is. And you have another one in the same stack that happens to require some of the functionalities in PHP 7+. Doesn't matter. The code is isolated in containers. The ways that those containers talk to each other is standardized. And as long as those standards are providing the service that's required at the performance that's required, there's no issue with that. You don't have to spend time and money and effort in trying to make sure that everything in your stack is adhering to the same version of everything else in your stack. You have many manual processes that are running, and these can be automated so that your deployments happen in an automated way. So you can utilize the best brains in the environment from us, let's say, right, to automate your manual processes, right, in the best way possible. That takes out a lot of the human errors that are made in deployments. Your solution can span multiple different data centers. That's very, very important. Your orchestration makes sure that the data centers are running correctly. So if one goes down, let's say you deploy across 2 data centers. One goes down, the next one will just spin up and take care of your load. Your system does not go down because you've lost a core component of your infrastructure. The environment is completely self-monitoring. The self-monitoring tools are absolutely awesome in this environment. The way that you get warned that things are maybe not going correctly is magic. You can now start doing preemptive management and not having to wait for something to fail before it happens. You can see, hang on, I'm starting to have a problem at point ABC. Maybe I need to mitigate that problem and do something about that risk. It's a highly available environment. You have scalability without downtime. So you can add to your application in the live environment while it's running without downtime. Your solution then becomes extensible, not only extendable. And that's a very, very important concept. It's a self-healing architecture. When things start going wrong, the architecture itself tries to correct the problem. This is a lot to do with parallel processing. Parallel processing has an immediate knock-on effect in bottleneck elimination. So if you've got one part of your stack dealing with authentication, and everybody tends to log in just before an auction, let's say, at that time, the system itself will automatically scale up that part, that Docker, that container that is dealing with authentication will be scaled up. It'll run multiple copies of itself. It will automatically redirect traffic to the right one, and it just keeps working. You don't run into a problem of waiting for things to come back. So it automatically scales itself. The service balancing and discovery on load balancing is absolutely enormous. It's an enormous thing to be able to see. Traditionally, in a monolithic architecture, you just see that the monolith is struggling. Here you can see which part of your whole stack is actually struggling, and that's a major, major advantage. You have control on automated deployments. The security is incredibly robust. You have now got the opportunity to set firewalls and proxies between various pods, and which are where your Dockers are running. You can set security at any level that you require to make sure that you're not hackable. The other big thing about this, as I've mentioned previously, is that if you get hacked, usually a hacker from outside only sees one part of your whole stack, and he's just looking at protocols going backwards, and he's looking at traffic, right? And the way we've done our security is he's got no way to actually understand what the traffic means because he's looking at one small part of the total solution. There's no single point of failure. You can design your environment in such a way that you do not have a single point of failure. There are many, many more advantages and benefits to running our kind of architecture. Right. Thank you very much for your time. The next steps is certainly for us to be able to interact with you and take you through maybe some questions you have around what we've put into this presentation, and then to engage you in looking at how we can make you a disruptive business within your sector. Thank you, and on behalf of As de Prier, right, we look forward to hearing from you.